So, welcome to module 7.1, and in this module we will be talking about virtual machine, the second part. So, in the last module we did talk about two classes of instruction, the stack arithmetic instruction and then the memory access instructions, and we also did a demo of the project 7. So, in this module we will go into the next two classes of instruction, namely the program flow instruction and the function calls. There are 3 program flow instructions and 3 function call instructions as a part of our stack based virtual machine, and what we will be covering now is the all those 3 in this entire module, and we will also be finishing off project 8 as by the end of this module. Now, first the easiest of the lot are the what we call as the program flow instructions, right. So, the program flow instructions basically have 3 in number. One is label, and they give a label, for example label loop, right, or right. So, how do we translate this? This is very straightforward. We have to just replace it by loop. This is the hack mnemonic, and the assembler will take care of resolving this. It will treat like a symbol and symbol table, etc. So, the next thing is go to label. Go to say some loop now, or go to loop. So, how would we this? So, we should say at loop is an unconditional statement. So, we say at loop and then say 0 : jump. This is the actual translation of this go to loop statement, right, and then if underscore go to some label. So, this is a slightly interesting stuff. What it does is this will check the top of the stack. If the top of the stack is having a 0, then it will do nothing. If the top of the stack is not equal to 0, then it will jump to the label, whatever label you have given here. So, this will jump to the label if the top of the stack is not equal to 0. If the top of the stack is equal to 0, then it just proceeds to the next instruction. So, this is the conditional statement, right. If the top of the stack is non-zero, then it is going to jump to the label. So, this is the if of underscore go to statement, and it will also importantly it will also pop the top of the stack, okay, right. So, this can be very easily implemented. Let me just go through the implementation. So, for this which we have done as a part of project 8. So, as you see here, right, as you see here, if it is just a label, we are just printing it as a semicolon followed by that label. If it is go to statement, go to some symbol, so we are putting that symbol here and doing 0 : jump. If you say if it's not underscore, it is if hyphen go to, then what we do? We have to first, so what will the stack, so what are the commands that are here? We will just copy these commands and then explain you in detail. For if hyphen go to, just copy this. So, at sp m equal to m minus 1, a equal to m, d equal to m, at whatever label d semicolon j and e, and that's it. Yes, that's it. So, this is what is if hyphen go to some label. The same label is copied here. The same label is copied here. So, what it does at sp at SP, so the stack pointer will be pointing to the empty location. There will be some location on here. I have to check if this location, say this is 101, I have to check if 100 is non-zero. If it is non-zero, I need to jump. If it is 0, I need to go to the next instruction. So where is SP in our RAM? SP is in 0. So 0 will be having, this is RAM 0. 0 will be pointing to 101, right. So at SP, means A will get 0, then m equal to m minus 1. So m of 0 is equal to m of 0 minus 1. So this 101 will become 100, right. So now your stack pointer will now start pointing. Anyway, we are going to pop this out. So stack pointer will be pointing to this 100. Now A equal to m of A equal to m of 0. So A equal to m of 100, which will be that value, right. A is equal to m of 0. So A will get 100. Sorry, A will get 100, and D is equal to this. This is what now D equal to m. So D equal to m of 100 now. So and this D will get the value. So whatever value here, some element E. So D will get the value E here, right. To repeat, my SP has now become 100. After that, I say A equal to m. That means A equal to m of 0. M of 0 contains 100. So A becomes 100. The next statement is D equal to m. D will be D equal to m of 100 now. Whatever is there in the A register is what is used. D equal to m of 100. So D will actually get an element. Now I set at label, whatever this label. So A will get this label now at this instruction. Now if D is not equal to 0, jump where? Jump to whatever is stored in label, right. So it will jump, otherwise it will continue. So this is how if hyphen go to label is basically implemented. So what we have seen is there are 3 program flow instructions, and all these 3 program flow instructions are very trivial, and this can be implemented like this. This is again a small revision if you had forgotten how to write equivalent assembly code. This is a small example of how we can code some ideas into hack assembly, right. Okay. Now the next set of instructions that we need to do is about function calls, right. So there are 3 instructions in function calls, namely the call, function name, and number of arguments. We call it as number of arguments that you are passing. Function, this is a function declaration, function name, and so in the book this is k and this is n. Okay, we will follow the same thing here. N is the number of arguments in the call, k is the number of local variables that you are going to use, right. So these two are things, and of course there is something called the return. Okay. Now to understand and appreciate how this call, function and return works, it is very important that we should also understand how programming languages handle function calls. So we will now take an example of how function calls are handled in C. The same thing for everything, many of the programming languages or almost all of the programming languages. So the programming language actually uses something called the stack. The system has a stack, right. So every time, so there is a function which calls another function. We have seen many examples of this. You would have seen many examples for this on your in your preliminary course itself. So there is a function which calls. There is a function which calls another function. This function is called the calling function, and this is calling some other function. That fellow is called the called function. Now let us look at this command call. Call is responsible for a transition from the calling function to the called function. This is call is responsible, and for the transition from the called function back to the calling function, the return is responsible, right. So, when we want to implement call and return as a part of your translation, we need to understand how the calling function transfers control to the called function and how the called function returns back to the calling function, right. Now, before proceeding further, so we will actually give an example of taking some code in C and show how these things are managed and what do you mean by transferring control from calling function to called function and what it means to return back the control, and all these things we will see through a very simple example. Right. What you see on the right hand side is a stack. Why do we use a stack? The thing will become clear in a while. Now, let us see main. So, it is a C program. So, there is main. The main actually has certain local variables AM, BM and CM, and now main is basically calling my proc, right. This is a function that it is calling. So, main is the calling function, myproc is the called function. To myproc, this basically sends certain arguments. Myproc returns a value which it assigns to VM. So, there are some arguments passed to myproc and there is a return value that myproc returns that comes back to main. And after myproc finishes its execution and returns a value, it should start with again back with L1. So, there is a return address. So, what happens is the calling function basically makes a call after pushing the arguments into the stack. It provides the arguments and then it calls myproc. After myproc finishes, myproc returns a value. After that, it starts exactly at the point where it left. So, after calling myproc, it comes here, it finishes after myproc returns, it comes and starts again from L1. Okay. Right. So, as far as main is concerned, it has certain local variables and it has certain arguments that it is providing for myproc. Now, myproc basically takes those arguments, it has its own local variables, it does certain computation, it finishes and returns back to L1, right, returns back to L1 because main has called. Now, when myproc is executing, now you see it is calling another function called nestsk1 for which it is providing parameters, arguments, and what happens is now nestsk1 executes and it gives back an answer back to myproc and it resumes its execution. So, myproc at L2. So, main starts executing, then it goes to myproc, myproc starts executing, then it goes to nestsk1, nestsk1 does the execution, it finishes, it returns a value and starts executing from L2, and L2 again now myproc completes its execution and returns back to L1 and then main starts executing again from L1. So, the last to be called, so who finished first? Main did not finish, myproc did not finish first, myproc in turn called nestsk1, nestsk1 finished first and then it was myproc and then probably it is main. Okay. So, the last in is the guy, last in first out. So, the last in is the guy who finishes the first, and so that is how the stack also works, right. So, stack also works on what we call as the last in first out policy, and that is why stack is being used for all these computations, right. Now, what happens? Initially the stack is empty. Now, when main starts executing, there is a space allocated for the local variables of main, namely AM, BM and CM. So, we are assigning AM equal to 2, we are assigning am is equal to 2, am equal to 2, bm equal to 1, am equal to 2, bm equal to 1 and cm equal to 1, that as you see here, right. And then what happens is that so these are the local variables of main, right. Now when main calls myproc, there is a return address and then it puts in certain arguments for this. So what are the arguments? So it is basically passing am and bm, where am is 2 and bm is 1, so it passes on 2 and 1, right. So when this call is executing, when it is calling, it stores the return address on the stack and then it basically passes the arguments 2 and 1, right. So this is now the argument section for myproc. Let me say MP. This is the argument section for MP and this is the return address for MP, right, and your stack pointer is here. This is what has happened when the call actually happens. Now what will happen when myproc starts executing? It will know it has 3 local variables. So like how local variables for main was allocated, there will be, so when myproc starts executing, there will be 3 local variables for myproc. So this will be your return address, this will be your whatever argument, and this will be your local address for myproc. So myproc will start executing, there will be a space allocated for fm, there will be a place there will be a place allocated, sorry. So this will be the local, there will be a space allocated for am, bm and cm of myproc. So this is a local, right, and then now myproc in turn now calls next is k1. So this is the return address for that, and now and it passes through parameter 2 arguments am and cm, am is 3 and cm is 6 when this is happening. So this will be arg for this, and then you will have arg is 3 and 6 for this, and then you will have basically what LCL. This is the local for nestsk1, right. Now nestsk1, when nestsk1 so when nestsk1 does, it completes, it finishes, right, it finishes. So what it will do when so that finished value it will go and store somewhere. So it goes and stores, so the finished value it goes and stores at this point. So now when it is finishing, this is all not any more necessary, because the function finishes, all the local variables etc. will take to go. So it will go and store its value in this first of the argument. So what happens is, if you note here, at this point you will get 18 next to L2, and then it will take the return address and it will go to return address. So it will start executing from L2, which will start executing, myproc will start executing now, and it will do. So when myproc starts executing, what should happen? So let us just go back. So this were the RIT, ARG and LCL for nestsk1. Now when myproc starts executing, your return address, your ARG and LCL should now point to this. So I need to go back to this stage, right. So when because then I will start executing myproc, so I need to go back to this return ARG and LCL, right, because I may be using the argument again, but when I am using it for myproc, I have to point to that. So this is basically called the context of your system. The next, so myproc executes and it finishes, and when it finishes, whatever value it is going to return, it's going to return 21. That 21 it will go and put at this point, if you notice, just next to L. So 21 is done. Now it will go to, now it will return to L1 and starts executing. Okay. Right. So this is how the function call is implemented. But one of the other thing that we need to keep in mind is, for all the local variables of the function and all the arguments, these are all basically loaded onto the stack, right. For certain elements which are going to be static, meaning they are not dependent on the function, they need to exist across function boundaries. Those are static variables which in our hack architecture will be allocated anywhere between 16 to 255. Anywhere between 16 to 255 in the memory, RAM 16 to RAM 255 it will be allocated. But for all the local variables and other computations, it will be allocated as part of the stack, and your stack normally is starting from 256 to a very large address, right. So when a function is executing, what happens is there is a frame created. So let us just go back and see what has happened. When main starts executing, there is a frame created where your local variables are there, and when myproc start executed, again there is a frame which says where you want to return, what are your arguments, what are the local variables, and then your and so on. So every time a function starts executing, there is some amount of memory allocated to the function in the stack. That amount of memory that is allocated to the function in the stack is called the activation record of that function. It is the memory that is activating the function. So this is called activation record, or we also call it as a stack frame. This is an activation stack frame which is responsible for the execution of the function. Now another important thing is, when main is executing, there will be some space in the memory which is kept for its local variables, its arguments and the return address. When we move from main to myproc, for myproc the return argument and LCL are different. And we move from myproc to nestsk1, then again your return argument LCL are different. So as and when we move from one function to another, the return address, the arguments where they are stored on the stack, and LCL changes. So when we go back, this is when I am calling. When the called function is finished and I am going back to the calling, now what should be stored in ARG and LCL? I hope you remember what is ARG and LCL. They are there in the memory, RAM 1, RAM 0, RAM 1 and RAM 2, which points to the argument and the local variables of that current function. So the ARG and LCL has to be, when I am executing main, the ARG and LCL of main should be there. When I am executing myproc, the ARG and LCL of myproc should be there in RAM 1 and RAM 2. When I am executing nestsk1, the local and this. So when I go back from nestsk1 to myproc, my original value of the ARG and LCL should be retrieved, right. So now that's called the context of the process, and we need to retrieve it. So when I am going from a calling function to a called function, not only we will push the arguments and we will keep some space for the local variable, we will also go and save the return address, along with that return address, the start of your argument segment and start of your local segment for the calling function. So when I am calling from main to let us say myproc to nestsk1, what did I save? I just saved a return address and I put the argument. Along with this return address, I will also say let this be 100, 101, 102, 103, right. So let it be like this, right. Right. So I will also go and save the ret ARG and LCL of my calling function, so that when I complete, I can basically retrieve that and starts executing, right. So that is very, very important. So this is how function calls work, and function calls use the stack, right. So, the stack is basically used by the function calls to create variables for all, to create memory, allocate memory for all its local variables, and then the return address. And when something happens, it basically happens on the stack, and when it completes its execution, it goes back to the calling function. And every time I am executing a function, its local variable, its arguments, the base of that local and ARG should be saved in the ARG and LCL space in RAM 1 and RAM 2, and that is possible if I have these ARG and LCL also saved in the stack, so that when I move from one function to another function, I can copy that ARG and LCL of that function into the RAM 1 and RAM 2, so that there is a seamless execution of this. So this is in some essence trying to basically explain you how function calls work, right. And we will use this concept that we have learned to implement the three functions that we are going to talk of, namely the call, return and function. Thank you. We will now meet now in module 7.2.